So in type 2, what we want to study, 0 to infinity px upon qx dx with the same condition as before. Qx is not equal to 0 and degree q minus degree p. So p and q, these are polynomials, and these guys, this degree is bigger than or equal to 2. Okay. So fine, that's the one which we would like to evaluate. So here I'm going to make two cases. So for example, here you see this thing can be like made to relate with the previous case. If, for example, I have my function to be an even function. Okay. So if px upon qx in this guy is an even function, then uh, I can say that 0 to infinity px upon qx dx, this quantity is half minus infinity to minus infinity plus infinity dx upon qx dx. Okay, so this is what we can say, and of course we know how to calculate this integral. So if that works out, that's good. But suppose that's not the case, then we will need a slightly different strategy. Okay. So of course, you need to remember that eventually I have to get this integral from 0 to up to infinity. So this one we will, as per the definition, that's limit r tends to infinity, 0 to up to r. Okay, so this is what we need to integrate. Okay, so let's see what we would like to do. Fine. So here, what do I want to do? Yes, Abhishek, what do you, which link do you need, Abhishek? Is it here or not? Hello, Abhishek, are you there? Seem to be here.
So
Okay,
he is saying for class link.
but he is already there in the meeting.
Yes, sir. Now join.
Okay, fine. Okay, so this is what we would like to do now. Okay. So let's see what do I do. So first of all, here what I want to do is the following. I would like to take what do you say? I would like to take a contour, and we will see how that contour helps us. Okay, so here what I'm going to do is that I'm going to like start with a contour which look like, which you will feel that okay, it might work out, but like things might not be there. We will see that there will be a problem, and then we will see how to rectify that. Okay, so we will see that. So let's do it. So let me draw the contour. Okay. So here, first of all, I'm going to have a bigger circle, and then I'm going to have another circle. Okay. Okay, and I need another ink. Okay, so what I am doing over here is that first of all I am, let's say, taking this to be some length m or some radius m, and this to be some radius epsilon, the small one. So the bigger one is m, smaller one is epsilon, and then I wish to integrate like this, like this, like this, and like this. Okay, so this is the path which I wish to take, and this path has some problem. We will discuss that. But this means what is the idea? As I said, the idea is to basically get integral of the form 0 to up to m, and then taking m to infinity. So, and I told you in the last lecture, while taking these kind of contours, you will see that managing things on a circular arc becomes quite easier. Okay? Because, for example, you know what's the length, you know how like polynomials grow. So, with all that information, it becomes relatively easy to deal with things on the circular arc. Okay, so if you think of taking this kind of contour, and you take your capital M tending to infinity and epsilon tend to 0, then effectively you can get the integral from 0 to up to infinity. Okay. Now the problem is that if I try to directly integrate my function on this kind of thing, so for example, here what we will get is that you will see that for this circular arc, like on this, my function, I can, for example, the length of the curve is 2 pi m roughly, or little less than 2 pi m, and my function is going to be, since the degree of q is bigger than uh, degree of p plus 2, bigger than or equal to, so the growth of p by q is roughly about is bounded above by 1 upon z square, let's say, or 1 upon x square in absolute value. So therefore, or here in case, therefore 1 over m square. So this one will be manageable. Similarly, now that px by qx is a holomorphic function, of course, it's non-vanishing on the real line. So therefore, what will happen is that uh, on this circular arc as well, my function is going to remain bounded, and the length of the curve is decreasing. So therefore, again, you will be able to make the contribution coming from that integral to be very small. Now the problem with this contour is that here, when you let epsilon tend to 0 and m tends to plus infinity, of course, this line segment that I have over here, that seems like giving you the integral 0 to infinity, whatever px upon qx dx. But the sad part is that there is this line segment over here, which is going to, again give me the same integral, but in the reverse direction. So that's going to give me sorry, minus of 0 to infinity px upon qx dx. So overall, what happens if I do a scenario like this or situation like this? So in that case, what happens is that these two integrals are going to get cancelled effectively, and therefore I am not going to have anything significant. Like my purpose will not be solved. Okay. So therefore, we need to find a way out. Okay. We first of all need to take a contour similar to this, and we also need to understand that since that on this line on the upper half plane and line on the lower half plane, since these two seem to be cancelling each other effect for epsilon small and m very large, we need to somehow introduce a new function which is going to help us in distinguish between the integral on the line on the upper half plane and integral on the line in the lower half plane. So this is where we are going to use our known function, like for example uh, log x or argument of x, these kind of functions. So if I let my argument vary between 0 to 2 pi, so you will see that on this line the argument will be close to 0, and on this line the argument will be close to 2 pi. So upon introducing that extra factor, what we will see is that the integrand, uh, although like the integral seem to cancel, but we will see that the integrand there is a difference, and because of argument or logarithm, whatever you would like to take, and therefore the effectively means we know that of course when things come around like around the circle, means around the circular path, things come back to the same position, then it gains an argument of 2 pi. Okay, so except for that argument of 2 pi, all other things are going to get cancelled, and then what will happen is that we will get the integral that we wish to capture. Okay, so let me therefore modify this contour little bit, and then do the proof. Okay, so let's see how I can modify this contour. So I have to read all this, but we will do it. So that's the play, and now of course I need to have this circular thing that's going to be there. I will also have a smaller circular thing that's also going to be there, but I also need this line segment. So what I am going to do, okay, so it seems this looks more like an SBI logo, okay, but somehow it got tilted. Okay, so that's my contour, or you can call it like keyhole contour example. So what's the process? I have over here, and then over like this, like this, like this, and like this. So here, for instance, what I'm going to do, okay, so exactly as before. So previously I wrote M by mistake. I was using R, so anyway, let's write R, and so that's the bigger circle. The smaller circle is of radius epsilon, okay? And I have, let's say, this width is epsilon square. Let's say that. So I'm going to take epsilon very small and small, and I have integral on this lines as well, I1, I2. So that's the contour that I have in this. And now, what can I do? So let me first of all write down again the line segments. Okay. So let's call this contour C epsilon R. So let's get that. Now, which function do I integrate? Like I told you, I want to make a distinction between the integral on I1 and integral on I2. So what I would like to do here is that, so we integrate integral on C epsilon R dz upon qz dz. So I want to integrate, dz I was not writing, so I want to integrate this particular function. Okay. So for that, as I said, I have to distinguish between I1 and I2. So I will introduce this new factor which is log. Of course, I told you you can take argument as well, but that's not a very user friendly function. So you know various properties about log, you know how to differentiate log and all that. So that's why we are going to introduce this log thing. Okay, and my C epsilon r is as in the picture. So I want to take this. Now, what do I get? So let's see. Uh, of course, from the picture, it should be clear is that if we let, so note limit epsilon tends to 0, r tends to infinity, integral over c epsilon r pz upon qz log z. This integral by Cauchy residue theorem is what? Can you tell me, anybody? Tell me what is this integral going to be? 2 pi I into some of the residues. So residue of what function, and where all the residues I should take? Tell me, what do I get here? Residue of, what do you think? If I just imagine, try to imagine that I am enlarging my R and I'm making my epsilon smaller and smaller. So then what do I get? What kind of like points will be the residues? Like they are going to come from where?
Whole complex plane.
Whole complex planes. So those are residue of the function pz upon qz log z and comma zk, where zk's are what? Tell me, zk's are,
Singularities in C.
yeah, singularities in C. So singularity of this function means what are those singularities? Like, do we have a singularity of log? Do we have a singularity of p? Any of them? So like, where exactly the singularities are coming from? They are
By
coming.
zeros of QZ.
Absolutely. Zk's are zeros of qz. So remember, from the first case, there is slight difference over here. This integral is giving, I am taking, in the first integral type 1, we were taking zeros on the upper half plane. This time, you have to take residue pz upon qz times log z. That's important. And zk's are zeros of qz. Of course, qz is a polynomial, so you have finitely many zeros. Fine, excellent. So this is what we get by taking this integral. Fine. Okay. So now, of course, this integral has several parts. This CR epsilon, this particular integral has several parts. So there is a circular path of radius r. So let's call it CR. So that has means that's part of the integral. Then you have C epsilon. So you have to integrate along C epsilon, and then you have to integrate along I1, I2. So means like so many things are there. So let's do one by one and let us see what's the outcome going to be. So we know what is the right hand side. We are going to interpret the left hand side in several different ways, like in several parts, and we will see what its value coming out to be. Okay, fine. Let's notice this. So by ml inequality, ml inequality. Okay, so what is log z? Actually, log z by definition we have seen this is log mod z plus I times argument of z, right? That's generally the definition of the logarithm. So therefore, when you take the absolute value, you effectively get the log of r and some plus something. So your argument is anyway bounded between 0 and 2 pi. So you can see that the log is bounded in absolute value, bounded above by log r plus some constant, and therefore what you have by ML inequality we get on CR. So CR is on the circle of radius r, whatever the circular portion that we have. There, this quantity, this integral is less than or equal to. Remember, the length of the curve is 2 pi r. Log of z is bounded above by, as I said, log r plus some constant, let's say c, and pz by qz, since degree of q is bigger than or equal to degree of p plus 2. So we have already seen in the last class, this is less than or equal to d over r square. Okay, so in effect, what we see, so limit r tends to infinity, integral over CR dz upon qz log z is equal to 0. So that says, like as I told you already, that the contribution coming from this segment is very minimal. So we will, since we can ignore that, that's going to become 0. Okay, fine. All that's fine. Now let's focus on uh, the inner integral. Okay, so the inner integral again by ML inequality. Okay, so again by ML inequality, if you think of taking this C epsilon Pz by Qz log Z, I want to, let's say, again, I want to understand this. So of course, again, the length of the curve is 2 pi epsilon, and here, of course, I don't have Pz by Qz less than 1 over r square, but here what I know is that P is a holomorphic function, Q does not vanish. So P by Q is a holomorphic function around 0. So Pz by Qz, it means like that's a holomorphic function or continuous function. So it's going to have some bound. Okay, so some bound, let's say. So you take some very small neighborhood, some delta neighborhood where Q does not vanish. So in that delta neighborhood, you get some bound which works. And anyway, you are going to take epsilon tending to 0. So that bound, whatever for delta positive you got that bound, same bound you can apply for any epsilon which is less than delta. So anyway, you are going to take epsilon tending to 0. So this is what this guy is. And then finally, log of z, that also, as I said, it's bounded above, like, so the value is log of mod z plus I times something. Now log of mod z, here mod z is epsilon on the curve. So log of epsilon, but as epsilon is very small, log is actually becomes negative, right? So this is actually, I need to write slightly carefully, log of mod of log of epsilon, let's say plus something. So whatever is that quantity, so your quantity is going to be bounded above by that. Now here you notice is that of course, this 2 pi epsilon times m times d, that one is easy to handle because that's just some constant times epsilon that will become 0. But moreover, you can also check that epsilon times log epsilon also goes to 0. Okay, so this is an exercise from real analysis. Check limit epsilon tends to 0, epsilon into mod of log epsilon is actually also equal to 0. Okay, so if you get that, then we see hence limit epsilon tends to 0, same integral over here. I'll write down this or just write c epsilon pz by qz log z, this quantity is 0 as well. Okay, great. So on both the circular arcs, my integral became 0. Okay, fine, all good. Now I need to figure out this integral along this path I1, line segment I1 and line segment I2. Okay, fine. So let's notice I said that this distance is epsilon square. So therefore, I'll draw this only the line segments slightly separately, and we will see how we can integrate. Okay, fine. So let's do that. Again, let us draw a small picture for ease of notation for our convenience. So effectively, what's happening? So I have to deal with, you see, I have to deal with integral along these two lines, let's say, okay, and this quantity. So these two quantities are epsilon, and this height that I have So this height is, sorry, I draw the picture. Yeah. So this segment, if I cross it here, so this segment is epsilon square by 2. Below is also epsilon square by 2. Okay. And I have a theta angle, let's say this is a theta angle, and I have to integrate first of all along this and along this. Okay, so these are the two integrals which I have to do. Okay. Now this is the picture that we have. So here notice, of course, here I drew theta. This is not quite required, but okay, I will just give the justification. So what is log? As we discussed, log is log of mod z plus I times argument z. Here I am taking my argument to be varying between 0 to up to 2 pi. Okay. So here what happens is that notice carefully that on this line, so let's call it, this one is I1, this one is I2. Okay. So first of all, note on I1, argument of z is maximum on the starting at the starting point. At the starting point. Okay. Because for example, so this is the starting point of your I1. So exactly at this point, the argument is maximum, because you take any other point of I, try to join the line, it's going to give you smaller angle. Okay. So the argument on any points in I1 will be smaller than the argument at the starting point. So that's the maximum value there. Okay. Now I know that if let's say if this angle is theta, I wrote already. So we maximum theta, say theta. Now what is this theta? So we get tan theta is equal to, what did I take? My length of the hypotenuse is epsilon, and the perpendicular is epsilon square by 2. So therefore what I get is that this tan theta is nothing but epsilon by 2, right? So that's my tan theta, and therefore, yeah. So if that is tan theta, then what do I get effectively? So as did I do it correctly? Tan is what? Sine is perpendicular by hypotenuse, and so yeah. So this is sine theta by cos theta. Let me just write that. Sine theta by cos theta. Okay, and of course, like as epsilon, you take smaller and smaller epsilon, your cos is going to, your theta is of course going to become smaller and smaller. So your cos is going to become close to 1. So your tan theta is roughly about sine theta, which is epsilon by 2. Okay, so therefore, what we see, so this is the tan theta, which is going to 0. So therefore, like what I can get is that as theta going to 0, sorry, and I just don't see anything. I can write from here itself. Okay, as epsilon goes to 0, theta goes to 0. So that's the more important thing. So if I take smaller and smaller epsilon, this argument is going to become smaller and smaller. So therefore, on this I1, let us try to see what I'm getting. So on I1, or rather, let me write, hence limit epsilon tends to 0, r tends to infinity, integral over I1 pz by qz log z. This quantity is becoming 0 to infinity px upon qx log x dx. So that's something which I get. Okay. Similarly, here I was talking about the argument in the positive side on upper half plane, its maximum and the starting point. And now, if you see the next, the on the integral I2, if I take points further and further away on I2, the argument is going to increase more and more. Okay, and it's going to go to 2 pi. Okay, so similarly, on I2, argument z is minimum at the starting point, and as epsilon tends to 0, the arg z, their argument of z goes to 2 pi. Okay. So that's the basic difference that we are encountering over here. Fine, all that is good. So therefore, what happens? So limit epsilon tends to 0, r tends to infinity, integral over I2 pz by qz over dz, or sorry, over times log z. This quantity is therefore, you see what's the direction of the integral? The direction of the integral is that it is starting at r and coming to 0, close to 0. So therefore, this is like minus infinity to 0 px upon qx, and this time my log is of course log mod z plus argument. So here it's log r log x plus 2I pi, because that's the difference in the argument over here. So this is the quantity that I get dx. Okay. So upon, it means once I come a full circle, I have an increment of argument 2 pi I. So therefore, what I can write that this is integral 0 to infinity minus px over qx log x dx. That's the first part. And the second part being minus 2 pi I integral 0 to infinity px by qx dx. Okay, all good. So if I add all of them, what do I get? So you see this quantity that I have over here gets cancelled with this one because there is a minus. And anyway, the contribution coming from CR and C epsilon, they were 0. So this one is already 0. This one was becoming 0. And this one, whatever the contribution of this one was coming, that got cancelled with this one. And this quantity also gave something extra. Okay. So if I put all these together, then what do I get? If I put all this together, then we get, hence, adding all of this, adding all these, we get, what do we get? We get that integral 0 to infinity px upon qx dx. So you remember that came only from here. So I have a minus 2 pi I, and that integral is by Cauchy residue theorem 2 pi I into some of these residues. So 2 pi I gets cancelled, and you have a minus 1. So this is minus summation zk, are zeros of zk's are zeros of q, and what do I have? Residue px qx, or rather pz qz, pz qz log z and z. So this is the integral that we are going to get. Okay. So that's the formula for this integral 0 to infinity. Of course, if I ask you to integrate such kind of things, all you need to apply this formula, carefully calculate the residues, and you will get the value of the integral. Okay. So you do not need to justify about all these lines and all that. But what I would like to tell you is that it is important to understand these contours in a way so that if there is a situation where which does not, let's say, fit into a particular type, then how will you do that? So in that case, this kind of experience helps you, okay, to do this. So this is one thing. So let me give you an example over here, and then we will go back to go to mistake. Then we will see some more cases. Okay, so let's do one example. Let's work out one. So, for example, I suppose I want to integrate 0 to infinity dx upon 1 plus x cubed. So clearly, uh, it's not an even function. So I have to, uh, apply only this means the formula for this case. So here let's first of all list down all the zeros of cube. Okay, so zeros of qz, so that's equal to z cube my plus 1. So what are the zeros? So for them, so are those for which z power 6 is equal to 1, but z cube is not equal to 1, because here I get z cube equal to minus 1. So I should have z power 6 equal to 1, but z cube is not equal to 1. So that means these are all sixth root of unities, which are not third root of unities. So therefore, like the primitive, uh, yeah, or which is not a sixth, which is not third root of unity, that is fine. It need not be a primitive sixth root of unity. But so therefore, what are the choices that I have? The choices are very simple. So we have e to the power 2 pi I by 6, e to the power 2 pi I 3 by 6. This is essentially like it's minus 1, but yeah, its cube is not equal to 1, so this is fine. And another one is e to the power 2 pi I 5 over 6. So these are the 3 points which are zeros of qz. Okay, so therefore what do I have to calculate? I have to calculate, so we need to calculate residue of log z divided by 1 plus z cube at the point e to the power 2 pi I by 6. So I have to calculate residue over here. And we have seen, of course, all these are simple zeros. So therefore, we know the whenever the pole is a simple pole, then the residue is nothing but a of alpha divided by b prime of alpha. Okay, so that's log of e to the power 2 pi I by 6 and divided by 3 e to the power 2 pi I. So 3z squared, so 2 pi I into 2 divided by 6. So that tells me what? So for example, I get log of this thing is equal to I pi by 3. In the denominator, I can clearly see that this is e to the power 2 pi. Okay, so let me see this. So I have a 3 over here, and I have e to the power 2 pi I 2 by 6. So if I multiply by another e to the power I by 6, so then in the below I will have e to the power I pi. So that's going to be minus 1. So this is e to the power 2 pi I by 6 divided by minus 1. So if I calculate, this is going to be I pi divided by minus 9, and I get what? E to the power 2 pi I by 6, that means e to the power I pi by 3. So that's cos pi by 3 is half, plus I sine is 3 by 2. Okay, so that's what is this particular residue. What about the other ones? So similarly, you can calculate. I'll write down the values. So the residue of log z divided by 1 plus z cube e to the power I pi already. So this one will be very simple. So that's log of e power I pi 3 into e to the power 2 I pi. So that's I pi by 3. Very simple. And in the second case, I again have to do the same thing. Residue of log z divided by 1 plus z cube e to the power 2 pi I 5 by 6. So if I consider this one, it's going to be log e to the power 2 pi I 5 by 6. Sorry, 5 by 6 divided by 3 e to the power 2 pi I 10 by 6. Okay, so that is what it is. And this time again I'm going to multiply by 1 5 over 6 in the numerator and the denominator. So what will I get in totality? I will have, let me just see, this is 10 over 6. So if I multiply by 2 pi I, so 15 over 6, will 3 get cancelled? So yes, so that will be 15 over 6. 3 will get cancelled. So 5 by 2. So e to the power pi by pi. So that's going to be minus 1. So here what do I have? I have I pi 5 by 3. I have another 3 in the denominator. And then I have e to the power 2 pi I 5 by 6. And I have a minus 1 over here. So that's 5 pi 5 I pi divided by 9 minus 9 rather, and then I have cos 5 pi by 3 plus I sine 5 pi by 3, and yeah, that is bigger than, so cos will be positive over there, so half minus I root 3 by 2. So that's the quantity I get. So hence I need to take the sum of the residues with a minus. So integral 0 to infinity dx upon 1 plus x cubed is equal to minus. I need to sum all the residues. So the first one is minus I pi by 9 into half plus I root 3 by 2. That's the first one, I think. Yeah. The second one being minus, or I pi by 3 plus I pi by 3 minus 5 I pi by 9 half minus I root 3 by 2. Okay, so this is what I am having. So you can try to see how what it comes out to be. I think most of the things with I, they are going to get cancelled, if I'm not mistaken. And what will remain is, let's see. Yeah, so okay, I have to calculate these things. So 5, 6 pi by 9, so that's 2 by 3, 2, 2 gets cancelled, 5 by 3, and here I have I gets multiplied, 2 by 3, 1 by 3, so that's 0. So if I put, yeah, so if I write this 3 as 6 by 18, then you will see this guy, and this guy will get cancelled. Okay, so this 3 terms gets cancelled. Because I can write 3 as 6 by 18, and that's what it is coming out to be. So that gets cancelled, and therefore what do I have? I have minus I pi, so that's root 3 pi by 18, and over here I have minus 5 root 3 pi by 18. So that gives me minus 4 root 3 pi by 18. So with another minus, this should be 4 root 3 pi by 18. So I can cancel 1, 2. So that's 2 root 3 pi by 9. Okay. So anyway, this is what you get in totality, and that's the value of the integral. Okay, so it's just an application of this formula, but having the knowledge how to do this is, of course, you know, good for you. Okay, so here, of course, the way I have done this, the same method, in fact, you will be able to use. So let me put a remark. The same method gives us, or rather can be used to find the integral a to infinity px upon qx dx for any a in R. So I can do that. So here, of course, as you saw, I was taking this integral from 0 to infinity, and I took this contour, this keyhole contour, centered at 0. Okay. And this time, what you should do is that you should shift the contour to center at, let's say, A. Okay. So if you have the same contour centered at A, and if you know modify your logarithm by log of z minus A, you will get that exactly the same analysis going through. Okay. And whatever estimates for epsilon r that we did, effectively, like up to a shift, everything works absolutely fine. Okay. So here, what we have, like in this particular case, the formula that we get is that here we have this integral a to infinity px upon qx dx. This integral is actually equal to, you can say, minus summation. Of course, as usual, zk's are zeros of q. We need to sum that. Residue of, this time, like I said, it was px pz divided by qz times log z. This time with log you have to be slightly careful, so this has to be pz divided by qz into log of z minus a at zk. So it just gets shifted to this point at a, and like initially we were having log z, which gave this change in argument once we went around 0. But now that the center is at A, so you have to, go around A. So if you have to go around A, so effectively, and then you want to have an effect of change in, argument, then what we essentially have is that you need to take this log of z minus A, so that it's like z minus A is uh, going around 0, right? So, if your z is going around a, and then your z minus a is going around 0, so therefore this is the formula when the integral is starting at a. So there will be absolutely no change in the proof, except that while taking some estimate, you have to be slightly careful, like some constant here and there. But at the end, finally, you are going to get this. So this works out exactly in the same fashion. Okay, fine. So that's good. That's very nice. And this same contour. So let's say this is remark 1. So this particular same contour can also be used in another case. So let's say mark 2, the contour that I have sent. This contour can actually be used. So of course we had seen px upon qx and all that, but we can think of working with fractional powers in the numerator as well. Okay, so because you see, for all practical purposes, I told you that you need, means in the denominator you need to have something slightly more than 1 to converge. Okay, so when you compare the degree, or like whatever the exponent of x in the numerator and exponent of x in the denominator you need to have something which is slightly more than 1. That will be good enough to ensure the convergence. Okay, so therefore you might think of taking fractional powers and all that as well. So the same contour actually works. So same contour works. So here I need to give you the formula separately. So stay back. So works for integral of this kind also, 0 to infinity x power alpha qx dx. So where alpha does not does not belongs to z, so this is not an integer, and I have degree of q minus the integral part of alpha is bigger than or equal to 2. So exactly like your alpha could be, for instance, your degree q could be 3 and your alpha could be 1.9. Okay, so the difference is 1.1, which is slightly bigger than 1, which is all I need to ensure convergence. Okay, so in other words, degree q minus the integral part should be at least 2 to make sense of the convergence. Okay, so now you had seen this in your tutorial sheet. Like you can actually take this square. Like for example, suppose I have alpha equal to half. So in that case, there is nothing but the square root function, right? So you already know how to define square root. So note that you this z power alpha is nothing but this is exponential alpha log z. Right? This is how you had defined square root of z. Square root of z is exponential half log z. So this is function that we have over here. Now here you can observe that I really do not need to introduce the logarithm anymore. Okay? Because for like all practical purposes, as you can see, in taking z power alpha, I am already having the logarithm in my picture. Okay, because as I go around 0, again there will be this log which will change value between 0 to 2 pi. So therefore effectively I will not have to, multiply by another extra logarithm or something like this. Okay, so I don't have to bother about that. So what do I have to bother about? So let's see what do I get. And so the contour is exactly as before. So let's go back to the contour and see it once. So let me just copy it there. So I have the same contour, let's say over here. Here, of course, you can notice that the uh, you know growth of q is as usual. Now, if you think of growth of z power alpha, then you take z power alpha in absolute value. So that's going to be nothing but mod z power real part of alpha. Okay, so that's trivial because here you will have exponential of real part of alpha, and then log mod z. Okay, and what do I have also? So yeah, anyway, so this you can work out and see that z to the power alpha is going to be mod z to the power alpha is going to be mod z to the power real part of alpha. So therefore, the growth that we saw for pz by qz, the similar growth estimate works, and you exactly know that degree of q minus integral part of alpha is bigger than or equal to 2. So therefore you will have degree of q minus real part of alpha is going to be, alpha is anyway real, so here I should not write this. So this is alpha actually. So alpha is already real. So this one I have. So therefore, what I get is that uh, the denominator is still having, degree slightly bigger than 1, and slightly bigger than 1 is what you need. So for example, if you come to this this over here, you see I had a 2 pi r over here. I had log, but anyway in this case there is no log. So here in place of 2, even if I would have had 1 plus epsilon, that would have been good enough to ensure that this limit is 0. So therefore really 2 is something which is, since we were talking about integer and all that, so we got 2 degree of a polynomial and all that. So therefore we got 2, but effectively you need something which is slightly bigger than 1 to ensure the convergence. So here, since already you have degree q minus integral part is bigger than or equal to 2, you get degree q minus alpha is strictly bigger than 1. So therefore the convergence on like the let's say on this circular arc, it becomes 0 exactly as it is. Okay, and also this inner circular thing, anyway it was 0 because my function is bounded, and the length of the curve is becoming smaller and smaller. So there also the function is becoming 0. So all I need to do again, understand integral on I1 and integral on I2. Okay, so clearly, as before, as before we have integral on CR and integral on C epsilon goes to 0 as epsilon tends to 0 and R tends to infinity. So this is exactly as before what we had, and all I need to understand is the integral on I1 and integral on I2. So on I1 as epsilon tends to 0, what is my z power alpha? Z power alpha is, remember, exponential alpha log z. So my epsilon tends to 0, we said as epsilon tends to 0, theta tends to 0. And since theta tends to 0, what do I have? If theta tends to 0, then your log of z is essentially becoming log x. Okay, so z power, this one is going to, this is log x, which is x power alpha. So that's the function what is becoming like. And on I2, as epsilon tends to 0, I have now z power alpha. So this is equal to exponential, this time alpha log z. So this one is log of mod z plus I argument z. So this guy is going to be exponential alpha log x, or it goes to alpha log x plus 2I pi. Okay, so therefore this is nothing but x power alpha into e to the power, sorry, there should be an alpha already, so e to the power 2I pi alpha. So that's the effect on I2. So therefore what do I get? If I add I1 and I2, I know that integral on I1 is from 0 to up to infinity. It's going to give me 0 to up to infinity. And integral on I2 is going to give me integral from infinity to 0. So what we get, hence we have the integral, or limit epsilon tends to 0, r tends to infinity, integral over c epsilon r of x power alpha, or rather, yeah, z power alpha by qz is equal to, so the I1 is going to give me 0 to infinity Remember what is on I1? On I1 I have x power alpha, so that's x power alpha qx dx, and on I2 I have x power alpha, but I also have e to the power 2 pi I alpha, and it comes with a negative sign. So 1 minus e to the power 2 pi I alpha times this integral. Okay, and this is what precisely I get, and this quantity by Cauchy residue theorem is exactly 2 pi I sum zk's zeros of q, and I have residue of z power alpha by qz zk. So here remember there is no multiplication by log, because z power alpha already has a log in it, which takes care of which distinguishes between the two integrals on I1 and I2, and it does not, immediately you cannot cancel them, so they are remaining intact. So as long as they are remaining intact, this is fine. So this is the integral we get, and therefore that gives you a formula for 0 to infinity x power alpha qx dx. Okay, so I can here also I can try to uh, do one example, and we will see some more cases after this. So let me see what else do I want to do. Do this too. Yeah, I guess this is fine. Okay. Okay, fine. So I will probably not have time to tell you about infinite product. So let it be. But these are more useful uh, formulas which we derive. So let's work out an example. So here I have 0 to infinity dx upon square root of x 1 plus x. So that's the integral we want to calculate. So this is 0 to infinity x to the power minus half 1 plus x dx. So that means you see in the numerator the alpha is minus half, so the integral part is minus 1. In the denominator the degree is 1, so the distance between these two is at least 2. So that's fine, all good. So by formulas, so by the formula above, what do I have? By the formula above, I have 1 minus e to the power 2 pi I. What is my alpha? My alpha is minus half. So this is minus, and the 2 goes away. So e to the power minus I pi, or pi I, times integral 0 to infinity x to the power minus half 1 plus x dx. That's equal to 2 pi I sum zk's are zeros of q, residue of this guy over the function z power minus half 1 plus z at and where the 0 is, here the 0 is anyway, I have only 1 0, so I don't really need to put a sum at minus 1. So this is the quantity which I have to find out. So once I get this limit, I will be done. Okay. So let us see this quantity. So 1 minus e to the power minus I pi, that's minus 1. So 1 minus minus 1. So that's 2. And over here, what's the residue? So the residue at z to the power minus half 1 plus z minus 1 I have to calculate. So I'm just going to multiply by z minus 1, and I have to uh, you know evaluate there. So that tells me what? So this is 2 pi I. Sorry, 2 pi I is not there. So the residue I have to multiply by z uh, minus minus 1. So that goes away. So here I have 1 upon square root minus 1. Okay. So that's 1 over I. Okay. This is what I get, and therefore in this case what do I have? So this implies twice integral 0 to infinity x to the power minus half divided by 1 plus x dx is going to be uh, 2 pi I into 1 over I. So that is 2 pi. Okay, so you could have told me that why did I choose this square root to be I? I could have taken the square root to be minus I as well, but then you will get that some integral of positive function will be negative, so that choice, is natural, that I will get I over there. Okay, so this implies integral 0 to infinity x to the power minus half 1 plus x dx is equal to pi. And also, otherwise, you treat your alpha properly, and then e to the power I alpha, you just accordingly substitute what is your function, and then you will get exactly which square root you are supposed to get. You will get it from the argument over there. Whatever is the argument, accordingly you will get it. Okay, so anyway, so this completes this type 2. So in type 2 we have done several cases. So the usual px upon qx dx 0 to infinity, that's taken care of. Remember, in this case you have to introduce this logarithm, because you want to separate or distinguish between the integral over I1 and over I2. That's the first thing. The second thing was that I shifted the center. It need not be at 0, so accordingly then you have to replace log by log z minus a, and exactly the same formula. And in the third case, where you can have fractional powers in the numerator or in the denominator somewhere, accordingly you can adjust. And then that fractional power, do not multiply log. I am repeating again and again. You need to understand where you need to put this extra factor. So if it is not required, why will you put it, right? Because if you introduce more function to the picture, of course they will distinguish, but they will help you to distinguish, but it will make also your calculations complicated. So in the case px upon qx, I had no way out, so I had to introduce. But once you have the square root of x, square root of or third root of x, and so on and so forth, in those cases, all you need to do is to understand that already logarithm is there in the picture. Okay. So we don't have to bother about putting an extra logarithm. All we need to do is to apply this formula, which I have taken without the logarithm. Of course, you can see here already there is an extra factor. This factor, so if my alpha is not in integer, then e to the power 2 pi I alpha, that's not going to be equal to 1. So therefore, this factor is a non-zero factor. So it's not going to be any problem. So you need to be careful about that, which formula you are trying to apply, that you have to be, like, you need to be conscious about what you are trying to apply. Okay, fine. So that's all good. Let's now quickly, I have 10-15 minutes. So let me now at least finish this business of integrals, and in the next class I can tell you about infinite sums. So I am going to integrate another type of function. So let's call it type 3. So it's not improper integral alone, but this time I am going to have uh, cosine and sine. So integrating, I integrate infinity minus infinity to plus infinity, px upon qx cosine x dx, and minus infinity to infinity px upon qx sine x dx. Okay. So I'm going to integrate, like, I will get this simultaneously, okay, as a result of what thing, and both these integrals will get. So because here we have the sine and cosine functions, so that gives you, periodicity. So you go up above the x-axis, come below the x-axis so many times. So only for convergence, it's enough to take degree of q minus degree of p is bigger than 1. Okay. So if you, some of you remember the Dirichlet test for infinite series, so there you will see that when you take product with sine and cosine, all you need is that there should be some factor which is taking it to 0. So uh, really what you need, degree q should be is bigger than degree p. That's good enough. You don't need uh, 2 degrees like degree 2. Degree 1 is good enough. So here enough to consider degree q minus, or enough to take, let's say, take degree q minus degree p is bigger than or equal to 1. So for convergence, that will be good enough. Okay, so if some of you are confused why this is enough, look at Dirichlet's test for convergence of infinite series. I have already told you this, that whenever you have improper integral of this kind, you should try to relate the scenario with infinite series. And so if you look at Dirichlet test, you will get that. Anyway, we will see that that should be enough also here. Okay, so what do I do here? So here also my contour is going to be exactly a similar contour that we have taken in type 1. Okay, so let me first draw the contour. Okay, so I have this circular path. So exactly like type 1, this is what I have. So what's my contour? My contour is like this and then like this. Okay, so this is minus r, this is r, this is I times r. So and let's call this contour to be gamma r. Okay, so here of course you can see that I can think of doing this integral exactly as it is, like we did in case of px upon qx. But the problem here is that the complex sine cosine, these are not bounded functions. So even though I know that pz by qz, how it grows, let's say even if I assume that degree of q minus degree of p is bigger than or equal to 2, even if I assume that, I will only know the bound for pz upon qz, and I do not really know how cosine is bounded. Like if I take a circle of radius r, how will I be able to bound the cosine? So that is something which is not quite clear, and therefore what we would like to do rather is that we would like to take, for example, because we have seen if I have exponential, anything which is exponential, I know how to take the bound. E power z is going to be e power x plus iy. So the bound of mod of e power z is just e power x. So we know for exponential how we can get bounds. So that's why I said that we are not going to treat these two integrals separately. Rather, we are going to integrate these two simultaneously. So we are going to introduce one function which takes care of both of them, and we will get what we wish for. Okay. Now cosine and sine, and I need a function. As I said, I already told you I need kind of an exponential function, which put together gives me sine and cosine. So that is e power ix, and here I am taking complex. So e power iz is the function that we are going to consider. Okay, so we consider the function or the integral over gamma r pz upon qz e power iz. Okay. Now e power iz, I claim e power iz is cos z plus I sin z. Can anybody tell me why this should be equal to true? Why e power iz is cos z plus I sin z? You can see directly from power series, right? Or for example, in case z is a real number, you know e power ix is cos x plus I sin x, and you know identity theorem tells you that if you have identity between two functions on a set uh, having a limit point, then the same identity holds true in a bigger region, right? Isn't it? So therefore we get this one. Now let's consider this integral, and here what we are going to do, we are going to show is that so the proof will be similar, and we will show that this integral, so we will show to get right, we will show, so first let me complete the formulas. So we will show that integral over gamma, or limit r tends to infinity, integral over gamma r dz upon qz e power iz is equal to 2 pi I into summation zk. So this is anyway obvious because of, there is nothing to show it. So by Cauchy residue theorem, this is equal to 2 pi I into zk's residue of p z q z e power I z zk. Zk's are zeros of q. So that's the formula, q on upper half plane. On upper half plane. So remember what kind of contour you are taking and what kind of singularities you are going to get. That you have to be careful. So pz upon qz e power iz, and the residue are to be taken at zk, where zk's are zeros of q on upper half plane. Okay, so that is there. So now here what I am going to do is that I am going to show that on the circular axis, again as before, this integral vanishes. Okay, so we show limit r tends to infinity, integral over semicircle of p z by q z into e power iz is equal to 0. So I show this. So if that's the case, then therefore this integral is only integral over the real line, right? And on real line, e power ix is cosine x plus I sin x. So hence we get integral minus infinity to plus infinity px qx e power ix dx is equal to 2 pi I summation zk are zeros of q on upper half plane, on upper half plane. So residue p by q, pz by qz e power iz zk. So that's the formula I get, and therefore if I need the integral of cosine, I will take the real part, and if I take the integral with sine, I will take the imaginary part. Hence integral minus infinity to plus infinity px upon qx cosine x dx is real part of the previous thing, and minus infinity to plus infinity px upon qx sin x dx is imaginary part of this whole thing. Okay, so whatever the residue that comes up, like this guy. So if I call it, let's say star, so this guy I call it star, so the real part of star, Okay, so therefore I will get the formula, and I all I need to do is to tell you how I can really show that on this circular arc the integral is going to go to 0. Okay, fine. So let's do it in two steps. So I is effectively, so here I will not have time to do an example explicitly. You can, I will just leave you some exercises. You can do it on your own. But let me just quickly complete this proof. So to show integral or limit r tends to infinity, integral over semicircle pz upon qz over times e power iz is equal to 0. This is what I have to show. So let's take the picture that side as well. Copy. Okay. I have, this is the picture, and notice over here that I introduce some real number h. So I am going to cut my contour into two parts. Okay, so I'm going to draw one. So let's say I'm drawing somewhere. Okay, I am going to segregate into two parts. So let's call this height to be h. Okay, so the part which is above this height h, I'm going to call it a. Part which is below is going to call, I'm going to call them b. So divide the semicircle circle into two parts. Okay. So what do I have over here? I have two parts a and b. So where a for real part of z bigger than h, b for real part of z less than or equal to h. Sorry, imaginary part. So I'm going to separate into these two cases. Okay, so what's the advantage of doing this? The advantage of doing this is the following. What's the this thing? E power, what's the absolute value of e power iz? Absolute value of e power iz is, you can write this is e power ix plus iy, and therefore this is nothing but e power minus y. Okay. So if your imaginary part is bigger than something, then this function e power iz in absolute value is actually bounded. Okay. So what do I have over here? So on a, if I want to integrate, so on a, let's say pz by qz on a e power iz, this in absolute value less than or equal to, of course, your function is c by r, that you know, length of the path is pi times r, and your e power I z in absolute value is bounded by e power minus h, because your imaginary part is bigger than h, so minus of imaginary part is less than minus of h, and that's the bound we are getting. So this quantity, you can clearly see that this quantity goes to 0 as h tends to infinity. So if I take h tends to infinity, it goes to 0, but of course h needs to be smaller than smaller in comparison with r. Okay, so what we are going to do is that we are going to take my h to be not very big, but not so small as well. We will take h to be square root of r. Okay, so take, we will see what is required at later, and then we will take. So on b, what happens? On b, I have integral over b pz upon qz e power iz. I need to integrate this. So this one, again, on p by q, I see that it's bounded by c times r. Okay, because here some constant times r, that's part of the circular region. Okay, and here as you can see that length of the curve, what is the length of the path? So this portion is almost proportional to h. Okay, so like for example, if your h is close to r, then you will get pi times r. So this is kind of proportional to h. So I can say that this is some constant, let's say d prime. I have used c over here already. So let me write c prime into c prime into d times h. So that's the length of the path. Okay, so this is not the part of the path. Just remember that this line is not part of the path. It's just that I am letting be there. I just is so it's just to indicate the height. That's all. Okay, so I'm breaking into two parts. Uh, the below part, there the length is some constant times h. So this one again, this one again goes to 0 as r tends to infinity. If we take, for instance, h should be smaller in comparison with r, but h should also go to infinity so that this guy goes to 0. So I can take, like I said, h equal to square root of r. Take h equal to square root of r. This quantity will go to 0 as r tends to infinity. This quantity will go to 0 as r tends to infinity. Okay, so therefore, what we see, so integral on semicircle pz by qz e power iz goes to 0 as r tends to infinity. Okay, so that sums up the proof, and therefore what we get is that this cosine, and with cosine and sine, what I have is that this is nothing but real part of the sum 2 pi I into sum of the residue pz by qz e power iz zk. Zk's are zeros of the upper half plane. Okay, so one thing I would like to tell you here very precisely, see, these are numeric questions. Okay, so often questions related to these things are numeric, so you should be very thorough with these formulas, and you should not make any mistake in exams or in any situations, because if you make some mistake over here, you are just going to lose out on marks, because these are just simple application. You need to calculate residues carefully, that's all, but application of the formula should also be done carefully. Okay, so that's it. I'll stop here. It's already over time. So here, let me just give you an exercise, and I will of course upload a tutorial a sheet where you will have more problems like this. So what is, let me ask you, minus infinity to plus infinity cos x divided by 1 plus x squared dx. This one, and what is again, uh, what is my 0 to infinity cos x divided by 1 plus x squared dx. Okay, so please solve these things, and with this I think this infinite integral that I wanted to, like improper integrals that I wanted to talk about, those are done. In the next class I will see how much I can do. I will try to do some infinite series, and if I have some little more time I will also tell you about this infinite product which I was thinking of telling, but we will see. Okay, so I'll stop here. You can tell me if there are any questions. I'll stop the recording, and I will also upload